Hello, 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 Ashton. Hello, Sulady. All right, hello, Remy from John Jay. Hello. Oh, and hello, Ariana. Hi. Oh, and I just missed. Wait. Oh, now it's coming fast and furious. All right. Good afternoon, Sylvie. Hello, Ariana. Hello, Kayla. Hi, Isabella. Hello, Abigail. Hello, Giselle. Hi, Dewan. Hello, Marina. Hello, Jonathan.
Hello.
Hello. All right. Good afternoon, Sue Lady. That was points right there. I meant, oh, what did you mean? Oh, okay, I see. Oh, I see. Okay. Wait. Oh, weird. Oh, I see. Okay, wrong. Okay, hello. Okay, hello, Catherine. I didn't say hello. And hello, who else? Kayla, did I say? All right. Oh, and the board. Goodbye, board. Oh, why? Why does that keep happening? Hold on. Because I really think we need the board today. We're going to get straight to things. Because I promised you, Remy and others last time, I promised everybody. Today we want to get straight to this homework that's been sitting in the docket forever. Here we go. We want to get straight to this homework because it's been like I say, it's been sitting there forever. All right, more people coming. Okay, there's Eugene. Hello. And here comes hello. Okay. And hello, Jake. All right. Oh, hello. Oh, want to let me know. Hold on, direct chat. Sorry. Okay. Yeah. Okay. Hold on 1 sec. I'm just responding to direct chat. 1 sec. Or did I already lose it? Okay. Okay. Excuse me. I want to get straight to this homework. So I'm going to try to not be boring, or I'll try to keep us lively. Again, I always, believe me, I know it's a long class, and it's long for me too, for electronic, and for the end of the day, it's rough. I know. And we'll try to mix it up and keep things. Oh, you're very kind. You said that publicly too. You're very kind. Thank you. Well, we'll try. We'll all, and you guys you believe me, you're making this much less torturous than it could be for all of us. We'll try to keep things lively. But the reason I'm saying all this right now is it has been long overdue that I've promised you that we need to go over this homework. So we will. So we're going to go over this homework, and it is a long homework. If we're not careful, I could easily just lecture about it for 2.5 hours. I don't want to do that, but I do want to go over it. I also want to make clear that now that we are going to finally go over it today, that means I did post the next homework. Let me be clear about that again. My grading procedures are perhaps unusual. They take a little while to get used to. Here's the deal. Like, the next homework is posted. It is technically due, a week from today. In some ways, depending on how you feel about math, it's more mathy. The second homework, it's math that we need to, there goes my board again. It's math that we need to do stuff. Some of you are comfortable with the math, some of you are not. We are going to review and refresh and relearn the math in a sort of physicsy way in this course. So don't worry. So what I'm trying to say is the second homework, some of you might find really easy. You might. Some of you might find it super annoying. Whatever the case is, I want you to know 2 things. Number one, the fact that we're up to the second homework now does not mean that you still cannot get more points on the first homework. Does not mean that I won't still be giving more feedback. I've even really given feedback. I've just given points to people that turned it in at all, and then people that turned in another revision or an improvement got more points. And that's always the way it's going to go. Like, anytime you turn in a draft, you get points. You turn in another draft of improvement, you get more points. I'm trying to get the points back as fast as possible, and I'm reading everything you're doing. but sometimes I'm giving you points back at the expense of, at the cost of extensive feedback. Hopefully a lot of the feedback is going to come in this class. Like you're going to see what I'm looking for in the homework and stuff in the classes, but I'm just telling you that as long as a portal for homework is open, that means you can always still submit. You can always still revise. And every time you submit, you get points. And every time you revise, you get more points. All of the points are there available to anybody, like literally even homework 1, even if you've never done it at all yet, you still could get all the points. But anybody who has already made 2 tries on it has already gotten those points and they're ready to move on to homework 2. So, I mean, so the good news is, like, again, there's no door is closed on anybody at any time to catch up. But the incentive to stay on top or to stay ahead, the incentive is just that, of course, you have less catch up to do. And that, it's just less stressful. But I'm saying all that again to say, homework 2 will be due next week. You make whatever attempt you make, you get a bunch of points. If you then need to make another attempt the next week and get more points, have at it, please do. And if you're still needing to go back to homework 1, please do. I hope that's clear. And the same thing is with me. Like, I'm just giving you the points as we go. Hopefully I'll give you more and more feedback also as we go, but everything you give me is a draft subject to improvement. Everything I give you is a draft subject to improvement. The only place this does not apply is once we get to an exam, then an exam is an exam. And we'll talk about that when we get there. But I hope that's clear. And if it's not, the mixed message I'm trying to send is, if you don't like a number that you've gotten on a homework so far, it's not a final number. I'm not saying anybody's complained, but if you don't like a number, it's not a final number. It even just means there's still more that you can still do. Or if you're pretty sure that that's not the case, if you think, wait, but I really literally did do every single thing, and I'm now listening in class and it seems like I did everything right, well, then tell me, text me. And then if I made a mistake, of course, no problem, I'll change it. But hopefully that's clear. Okay, I'm going to look. But so now what we're going to start doing is going over homework 1. That's what I'm saying. We're going to start methodically going over homework 1. You can use it to improve whatever you did before if you need to, or if you don't, you don't. I got to fix the board again. The board keeps going. Hold on. And I see there's stuff in the chat. I will look in the chat. And the other thing is, I'm doing all this. So we're going to be very homework oriented today, like lecture oriented. You still should participate as much. I mean, you do anything you can to stop me from just lecturing. But we're not going to talk much about lab today, because I'm still assuming, wait, am I wrong about this? Wait. Yeah, right. Like this coming. Oh, we do have to talk a little bit because you have lab on Tuesday. Right. Okay. Yeah, I'm not changing the plan, but you may have to remind me that by the end, I will have to say something about lab, because yes, you have lab. That you don't have lab next Monday, but you do have lab next Tuesday, which is weird. So we have to do something about that. Okay. Last thing also, before I forget, and I will look in the chat, apparently last week I totally forgot to give you a game turn. I don't know how that happened, or I think I did. So you may have noticed that the game turn, just the 2 minutes of participation thing that you do for 5 points, I somehow didn't post that last week. So I'm going to ask, just right now, take a minute right now before we get rolling to reflect on however you participated last week, even if you just said hello. Just take a moment to do it. Like, that's why it says do 5 o'clock, to remind me and to remind you. Let's just get last week's out of the way right now so you can get 5 points. And then we'll be back on track. Tonight's that's due at midnight will be for today. I hope that makes sense. So take a moment right now to look at what should have been game turn number 3. So confused, right, from last week. Hope, because it just got posted, and it says it was due at 5 p.m. just so we could just do it now. So please do that for a second while I get my head together. Let me just. Oh yeah. Oh wait. So in the chat, should we submit the if you have a revised version of any homework, you can submit it at any time. If you're asking me in the chat, if Ariana is asking me in the chat, like after we go over the homework today, if that causes you to make revisions on your homework, if you're asking, can you submit right after class, even based on what we do in class? Yes, absolutely. You can submit revisions at any time, including after class. Yes, I'm not saying you have to, I'm just saying every time you submit a revision, you get more points, that's all. But yes, what I am asking now, am I making sense that the game turn, I forgot last week, and is Eugene, does that, or whoever face I'm seeing, does it make sense? Can you just do it right now, the game turn from last week? Oh, it makes sense. Okay, thank you, Caleb. Ooh, Caleb, that's helpful. You just got points for that. Thank you. All right, you do that for a second. I'm gonna get my board reset up again here. Okay. Oh, that's interesting. Catherine's question. Huh. It's funny. You think that's a good question. Catherine's question about the the MSRC. I'm willing to open up a portal for that. Sure. I don't know why that doesn't come up a lot. Well, partly. So do they have a tutor for this class in the MSRC? They do. Huh. Okay. Sure. Remind me. Yes, I'm happy to do that. I don't know why I didn't think about that. I'm happy to open up a portal for that. I may ask you to remind me, either when we have a down moment in the middle of this class, like because I'm a little bit scattered right now. It takes me a minute to make a portal. So either remind me, or if you send me a text, like at some point outside of class, I will set up a portal for that. I'm perfectly delighted to do that. I will tell you right now, if we're going to do that, it's funny. If we're going to, I'm happy to give points for going to the MSRC, but I'm going to put in the portal that I would ask you to tell me who your tutor is in the MSRC if you do that, not be, just so I know. I mean, just so I know. I won't talk to them about you or anything. I won't, unless you want me to. But it's good for me to know who's tutoring what and who, I mean, because anyway, so yes, sure. I'm glad I didn't. A lot of times they don't have a tutor for this particular class, which is why I didn't think of it. But sure, yeah, okay. Anyway, good question. Okay, can I just ask? Let me just. Okay, I'm getting myself already. Oh, thank you. Oh, and she just closed the loop too. You realize just for that little conversation, you just got like. I hope you realize that there's like a million portals open where you can get points for just that conversation. And yeah, remind me. I'll definitely open up a portal. That's great. I love when people say thank you. All right, what I'm going to do right now, I just want to see that we know what we're doing. Oh, you all did it. Thank you. You all just did. You're actually totally with me. Okay, so 13 of you. So thank you, Isabella. Thank you, Sylvie. Thank you, Sue Lady. Thank you, Abigail. Thank you, Ashton. Thank you, Kayla. Thank you, Eugene. Thank you, Jake. Thank you, Marina. Thank you, Jonathan. I mean, I'm assuming you just did this right now, right? I'm not totally confused.
You're welcome.
Yeah, okay, great. All right. And you just got points for voice. Awesome. Thank you, Giselle. Thank you, Dewan. Thank you, Fatima. And whoop, I just messed it up. And there's 5 others. And yeah, and okay, well and hopefully, and I don't mean this person, but hopefully the rest of you, like Nicole, Ashley, Catherine, Ariana, Remy, hopefully you understand what I'm saying right now, and you can just do it quickly when you get a chance. It's just free points. But okay. Then what I want to start doing, I want to start going over homework 1, like I said. I'm just looking in the chat. Oh yeah, and don't overstress. I mean, right, because usually this is why I like to turn these things in by midnight. It's my bad that I didn't put out the portal last week. And this is exactly why it's my bad. Like it was a whole week ago. So don't kill yourself. Even if you just remember saying hello, that's fine for now. I just want to keep on track with these things and not fall behind. But don't kill yourself over it. Because I get it. I'm just glad you understand what I'm saying. That's good. All right. So I'm going to turn to homework 1B, a thing on a spring. And I'm going to go over it. And we're going to do some physics here that we haven't talked about yet. We're also going to show you sort of my procedures for solving physics problems. So it's going to take a little while. And I'm going to show you the procedure for solving physics problem that I highly recommend, that gets you the most points possible, that maximizes the chance of not only getting a right answer, but justifying your whole thought process and showing all your work, but also I want to show you the method that I think maximizes your chance of having something to do even when you don't know what to do. Like which really is the purpose of physics education, right? Really, we're not here to give you knowledge, because frankly, we got Google for that. Right. And we got Khan Academy for that. And we got like the whole worldwide friggin' web for that. Right. Like you at this point, really, if all I gave you was information and knowledge, I really would be wasting your tuition dollar, because really you're much better at going out and getting information and knowledge on your own, really, than I am in giving it to you, especially in this stupid format. The best thing that I can give you as a physics professor is to teach you what to do when you don't know what to do, right? That's real science research. What do we do when we don't know what to do? Right. And part of the purpose of these homework problems, especially having them assigned before we've like had a bunch of lectures and stuff, part of them is to get us in the habit of just that, of actually having tips and techniques and tricks for thought processes, to begin thought processes, even when we don't know where the thought processes are going to land. Okay, so what do I mean by that? All right, so here's the problem, right? The thing, hopefully you have the sheet in front of you. Like I can't switch back like 3 screens back and forth while I'm doing this. But so I've written out the diagram from the sheet. We've got this spring on one end attached to a wall, on the other end attached to a mass. The spring has a stiffness constant of K. It has a mass of M. The spring mass is pulled out to an initial position, an initial displacement from equilibrium known as X naught. Equilibrium itself, the equilibrium position itself, is defined to be X equals 0. And then we happen to actually provide the numbers for you. We happen to tell you that K is 200 newtons per meter. We happen to tell you that the mass is 0.3 kilograms. We happen to tell you that the initial position is 0.15 meters. Great. So we're going to end up plugging in those numbers for sure. But I also want to clarify or point out that those numbers are like the least important detail of this whole problem. Most of the physics that we're going to do on this problem is about what we would do to constant values known as K, X naught, and M in general, whatever numbers they happen to be equal to, right? So we're going to try to provide and manipulate equations that involve those letters for as long as possible. And then at the last minute, plug in the numbers. The first question that's asked on the sheet about this diagram, the first question is the first question is at X equals X naught. What is the force being exerted, right? Stop me if that's wrong, but I believe that is the first question on the sheet. Now I want you to know that what I've already done by drawing this diagram and writing out this question, I've already done 2 steps of what I would call the 5-step physics problem solving procedure. Okay, I'm going to outline that procedure for you right now. And this is what you would use for any homework going forward, and certainly what you would use on exam when we get to them. You would solve all your problems on a separate piece of paper, just like we're doing now, right? Like you have the sheet, that's the problem itself, that's like an exam booklet. Then you go to separate blank pieces of paper and you start writing things out as though they were a blue book. Okay, so here comes the 5-step method for solving physics problems. Step one, and obviously I do hope you're taking notes on this, but step one is called DFP. The first thing we do when we're solving a problem, and I just did it already here, I'll show you, is we draw out the diagram. And you know, you could really call it, it doesn't have, I'm calling it a diagram. It doesn't have to be a technical diagram. I don't mean a graph. I don't mean a free body diagram. I don't mean necessarily a specific, I don't mean a vector diagram. I mean a picture of the situation, just like the problem, our homework problem here provided. Sometimes homework problems do provide, sometimes exam problems do provide pictures, sometimes they don't. I'm saying no matter what, if I'm solving a problem, I've got to draw one. Mine, the one that I draw might be very similar to one that's provided, but the key purpose in drawing the picture is to provide the facts. It's not to solve yet. I'm not solving anything. I'm drawing the facts as I know them, the given facts, the given information, right? And how, and specifically, the whole purpose of a good diagram is that the labels in the diagram define all the constants and variables that will be used in the math that is going to solve this problem. In other words, the real what's going to happen when I start getting into solving the problem, I'm going to start having a bunch of equations, right? A bunch of things like x minus x naught equals whatever, like v minus v naught over t equals a and blah, blah, and then I start rearranging it. I cancel out the v naught and I plug in this for that. But the point is, what the heck does v mean? And what the heck does t mean? What do they refer to? All of the letters that I'm going to use in solving the problem are going to have definitions that are clear to the reader, because all of those letters will be sitting there as labels in my original picture. The point of a picture really is to define all the terms that we'll use to solve for the rest, okay? So I'm saying first, we provide a picture, and that's what I just did right here. And again, I might have been already provided in the problem, but I do it, and I don't copy and paste, and I don't, the board just disappeared. Okay. I literally do it, but with my own hand, even if I'm copying, because I find that doing it by my own hand, I will begin to understand certain things about the problem that I would not otherwise if I don't do it with my hand. All right, so here we have the picture, right? And we see everything's labeled like M. It's clear what M means. It means the mass at the end of the spring. K means the stiffness of the spring. X naught means where the mass is sitting right now. X equals 0 means where the equilibrium of the spring is, right? And then right next to it, I said what those letters are equal to in terms of numerics. That sometimes is provided, sometimes it's not. But I've got a picture that is defining the terms of my problem. That is step one. And I'm telling you right now, also, I know I'm yelling because I'm trying to be lively, but I'm yelling at the risk of boring us or condescending. I know you've solved a million science problems in your life. I know that. And I know that you're always told to show your work. What I'm trying to say right here is we don't just show our work to justify things. We show our work so that we can get our work going, especially when we don't know where it's going to land. What I'm saying right now is if you do this 5-step procedure that I'm showing you, each step you do gets you full points, even if you don't know the final answer, or even if your final answer is wrong. Okay, so first you do this, and this is really actually the way I grade, particularly exams. First, you would draw your own diagram with labels. That is step one, DFP. And it is the diagram and fact pattern. It is the facts that are going to be given and used in the problem. Okay, so that's step one. So we've done it. So we've done it. All right, so we've done step one. Step two. Step two is WIQ. This is possibly the most important one. It seems like the most obvious, easy one, and it's the one that people skip all the time, and it's crucial. So step two is you jot down the question. Now, let me be clear about this again, too. All of homeworks are practicing of this method, and the harder the homeworks, the more important this method becomes. But it's all practicing so that you do this on an exam, right? And so let's be clear. I know I gave you a problem sheet that has the questions on it. I mean, I wrote the questions out. I know that. I'm telling you, believe it or not, that when you go over to your own blank white pieces of paper or in exam, your own blue books or whatever, like it's crucial that you write out your own version of the question. You know, it should be a distilled, summarized, short version, a version that, you know, is in your language, that's abbreviated. This is not about copying and pasting my lengthy question. It's also not about you trying to scroll your answers onto my sheet. This is all assuming that and this is what most of you did, by the way, which is good. This is assuming that you've like set out your own pieces of paper to do stuff out. But now we get to question one on this sheet. On the actual sheet, it said all this English. I could screen share in a moment. It said all this gobbledygook, like at the initial position, what is the force exerted by the spring? I'm saying that what you do is what I just did right here. You just write, okay, question one. So you draw a diagram, right? We've drawn the diagram. So this, okay, let me be clear. So I did step one on this page. Here's my step one. Diagram and fact pattern. I did it, right? Now, the next thing I do, step two, WIQ, I literally just wrote at X equals X naught, comma, F equals, question mark, like that's the question. I've distilled it down to its essence. I've on purpose made it short and simple and sweet. If I'm the student, I make it like short and simple and clear, but I make it clear to myself and to the reader that I know what the question is. And I'm going to really harp on this. Believe me, in a few minutes, it sounds so easy and stupid, but right now, trust me, it's just free points. If you do this, if you write down the question, you're getting points for that. So step two, WIQ. Also, by the way, when I'm grading carefully and thoroughly and stuff, especially exams, what I'm telling you right now is also my grading rubric. Like if you were getting an exam back or something, and you're looking like, what happened? Well, why did I lose points here? What if you just see off in the corner like -2 WIQ? That's what it means. I'm saying you lost 2 points because I don't see what the question is. Like, you got to tell me what the right. So this is also just like where people gain or lose points. And you notice so far, you don't gain or lose points for any inaccuracy of answers. You're gaining or losing points for doing a thought process that goes according to this structure. So, okay, so all these stupid acronyms are partly to just help you remember, but they're also just acronyms for grading. Like step 2 is WIQ, what's the question? So you just summarize you distill the question down to its essence like that. Then, okay, so we've done step 1 is DFP. Step 2 is WIQ. Then comes step 3. Now we're starting to get into, oh, did I just, okay, hold on. Sorry, God, thanks. Okay, so step 3. GDP. Yeah, that does not stand for gross domestic product, although I mean, I suppose that's what, oh my God, what is happening? Okay, that does not stand for gross domestic product, although it might sound like that. What it stands for is general definitions and principles. Now, this is where things get a little bit interesting to me too. This is, again, I know some of you are thinking like, my God, what does he think? We're in 6th grade, like we know how to do homework. And yes, you do know how to do homework. I'm telling you a sort of specific sequence that is right in here is about to get more specific, maybe not the way you always do things. Maybe it is. But step 3 is you're now going to write down, well, just that, general definitions and principles. That means specifically what I'm asking is now for some kind of truth or truths that are true in general. Oh my God, sorry. That are true in general, even before we sat down to solve this question, that are true whether or not this question is being asked. In other words, x equals 0.15 or x naught equals 0.15 meters. That is a given. That is a given in this problem, and it is true and it is important, but that's not a general truth, right? It was a fact that was laid out in step 1, that in this case, the initial position or displacement of the mass is 0.15 meters, right? That is a fact. It is true, but it's only true specifically in this problem. It was a given of this problem, and that's kind of why I was put in the diagram to make it clear what's going on in this scenario. But now in so then we were presented with a scenario, step 1. In step 2, we're being asked a question about this scenario. That's step 2. Now in step 3, in order to start answering this question, we're stepping back and we're thinking about anything that we know that's true in the universe, whether or not this question is being asked. Okay, and obviously I'm going to give you an example in a moment, but an example. So here in this problem, so if we're doing question 1 in homework 1B, remember, I was just asked about the force, right? I was asked at the force, what's the force being exerted at x equals x naught? Well, a general truth for that, well, in fact, I'll say, Okay. In short, what I'm saying here, well, the short version of what I'm saying here is the big example of the GDP of step 3 here will be F equals negative KX. The equation, step 3 GDP is usually looking for what I print definitions, principles, laws, equations, what you might call formulas. I don't really like the term formula personally, but whatever it is that you consider formulas generally would go here in step 3 GDP. GDP is the type of equations or formulas or laws or definitions that we need to solve this problem, but that are true whether or not we're asking this problem, right? So in this case, Hooke's law, first spring, F equals negative KX. Now I wrote it out in a little bit more detail right here, just because I'm trying to be clear. I mean, you don't have to get this detailed. The main point is F equals negative KX. I'm saying that that's a law that applies to any well-behaved spring. And then I'm sort of being specific about what I mean by well-behaved. Honestly, I don't even know why I'm doing all of that. The point is F equals negative KX. That would be an example of a step 3 GDP. As problems get more and more complex, there may be many, you may have to write 1 or 2 or 3 things down for step 3 GDP. But I want to say a little bit more, but I want to say a little bit more about step 3 GDP. Okay. I don't know if I've mentioned this specifically to you before, but I want to say right now, there's 2 types of equals in math and science. There's double equal sign, like 2-bar equal signs, and there's triple equal signs. It's actually really super helpful to maintain an ongoing distinction between those 2. If you use a triple equal sign, you're saying that 2 things are equal by definition. Like we declare them like average velocity is triple equal sign equal to displacement over time. Average velocity is defined to be displaced over time. If it's true at all, it's always true. A triple equal sign is a very strong, powerful equality. If a triple equal sign is true at all, it is always true. If a square is a rectangle with 4 equal sides, then it always is, and you're never, ever going to find a 3-sided square. Or you're never going to find a square that has 2 sides unequal. Never. Because we didn't find out in the lab that a bunch of squares happen to have 4 sides. We're just saying that anything that has 4 sides that are equal and 4 angles that are equal, we're calling a square. So if we're ever right to do that, we're always right to do that. Triple equal signs are equal by definition. If they're true at all, they're always true. Double equal sign means it's equal by discovery. We found out by looking at a bunch of data that something basically seems to be equal. Those can be largely equal, but not perfectly equal. Those can sometimes be unequal. Those can be proven wrong, et cetera, but triple equal signs cannot. So ideally, what we're looking for in step 3 GDP, we're ideally looking for definitions, things that are just true. Either way, I'm going to say one last thing. What am I going to say this? Well, I'll go on. All right. So in step 3, we write down a general truth. Let me point out again, by the way, this whole method is only a 5-step method. We're already up to step 3. And notice, we haven't solved one freaking thing. We haven't done one computation. We haven't crunched one number. We haven't scratched our head really to work anything out. And we're already past step 3. That may seem weird to you. I don't know what it seems to you, but deliberately, I'm saying that this method of solving problems in physics is very top heavy in that there's a lot of preliminaries we do before we even start crunching numbers. What I'm really telling you is that even when you get a problem, as things get harder and harder in this course or in life, in science, as things get harder and harder and more things, we're looking at things, we're like, I don't know what the answer is to that. I don't even know how to get the answer to that, whatever that is. I'm saying there's a bunch of things we can do before we even try to get an answer that at least in this class, you get direct points for doing. Now, I think that's because even in life you do, whether it's direct or not, but there's a bunch of things you can do before you even start crunching difficult things that really set you up for success. So the first thing is you make a diagram. The second thing is you actually literally write out what the question is. As dumb as that seems, it's so important. It's beyond belief. Because, okay, actually I have to sidebar that for a second. I don't know if you've had this experience. I think you all have. I certainly, many times in my science student career, many times I got an assignment or an exam where I sat down, looked at the thing in good faith. I looked at the question and I was like, are you kidding me? Wait, I studied, I didn't rob any banks. I didn't knock any old ladies over on this. Well, that's weird. Why did I just say that? Whatever. I'm like a good person. I studied. I thought I knew what was going on in this class, and now you're giving me this exam, and I'm looking at the question. I'm ready to go. I literally don't even know what you're asking. I have no idea what, I literally do not know what to do. What does this question even mean? I don't know if that's happened to you, but it certainly used to happen to me a lot. And what I'm saying is actually, and that gets very stressful. And then I tighten up, and I don't know. I have nothing to say if I don't even think I know what the question is going. So one trick to that is in fact, before totally tightening up and collapsing, is to actually write down, just to try to write down what you think the question's asking at best. So, because if I try to do that, I can go step by step. I can find out that, okay, I'm going to get myself on a whole tear, but often I'll look at a question and go, I have no idea what you're asking. But the thing is, that's not true. I don't have no idea what they're asking. What actually it is I have some idea. Oops, someone's here. Hold on. Sorry. What actually usually happens when someone's asking me a question is I have some idea what they're asking, and I have some not idea of what they're asking. They're using a bunch of words that are kind of familiar, that I was kind of expecting, but then there's 3 or 4 words in there that I don't know what they are. And they're making me so frustrated with the whole thing that it's all becoming a fog. So in fact, what I should do is start writing out what I think the question's asking until I get to those words that I don't know. Then I realize those are the words I don't know. Then I can look up those words, right? This is all all of this, but I'm saying that usually we have more of a clue than we think. But the minute we sort of don't have a clue, it becomes I have no clue. So it's really important to isolate the things we know from the things we don't. There goes my board. So the actual act of writing out what you think the question is, including the words that you don't understand, then at least forces you to see which words you don't understand, and then you can look them up and you start making, you get my point. So then you write down what the question is. That was step 2. I'm putting my board back. Then you start writing down equations that are actually germane to the whole topic. Okay. And by doing that, you're already up to step 3 of this method. You haven't even had to crunch anything, and you're already getting points for every one of these steps. Now I'm just putting the board back and we're going on. Okay, so now step 4. Sorry. Step 4. Here we go. I thought. Yeah, here we go. Okay. So then step 4. Is PAW, P-A-W, like a dog, like woof. But what does it stand for? It does not stand for woof. It stands for, oh God, there goes my dog. I'm sorry. Okay. But it stands for okay. In step 4, we're now going to start applying the general principle to the particular example of this problem, right? I'm going to explain this. Did I just lose the board again? Actually, sorry, I'm just gonna put this on the next page because it's too. I will recopy that. It's getting too crowded down here. I'm just saying right here, we're now going to start solving the problem. Oh, someone's here. Sorry. This is where we're going to start doing the algebraic computations and calculations. In fact, okay, I'll do it here for this problem, and then I'm going to make some comments about this. So here, right, and now obviously by the way, I know I'm hitting an ant with a hammer here. Like I'm doing all of this work here just to do question 1 of your homework. And I know question 1 is just a plugin, or I think it's just a plugin that you might have done in 1 line. And I'm stretching this all out because I'm trying to show you the procedure that is easy to see when it seems unnecessary to do, but I'm showing it to you now so that you have something to do when it is necessary to do. Okay, I mean, it's a little bit of overkill on a 1 moment problem like what's F. It's a little bit of overkill, but it's not that much overkill. Anyway, so I'm showing you. So in other words, right here on question 1. So here. Oh, wait. Oh, yes. Oh, great. Thank you. Yeah. So here, I'll back up. So what PAW stands for is sorry, I'm just getting this. It stands for it stands for particular application and work. Okay, so this is where we get particular. Like step 3 was general. Step 3 was some big truth that's just true in the universe. Now we're going to narrow down in step 4 and apply that big truth to the particular, we're going to apply to the particular details of this problem. And this is where we're going to show our work, so to speak. So PAW is particular application work. I'm glad you, particular application and work. I'm glad you asked. And in this case, as an example, what I mean is, oh, great. Thank you. And see, she said, thank you. And it's not, which is so polite and nice, but also she said, got it. So now I know she got it. So now I can move on, but instead I'm talking about it. So I'm not moving on. So that's super annoying. Okay, so I will. Okay, so here I'm saying like, here, okay, so here is where we're doing the work, right? I have a couple comments, but like this is where we're doing the work, like we're plugging in, so to speak, right? We're solving the problem finally at step 4. Again, notice we only just started actually solving at step 4, and there's only one more step, which is circle your answer. So step 4 is a big one. It's, it's like there might be a lot of computations and calculations going on in step 4 for any kind of slightly harder problem, as you'll see in the rest of the sheet. But I want to make some so I want to make some comments about this though. Okay, notice first of all, we're proceeding as we're solving this problem. And again, I know that this problem is comparatively straightforward, but notice how we solve this problem is we proceed from what is true to what is relevant, rather than the other way around. What I'm saying is, when a problem is easy, it's easy to see, and I shouldn't keep saying easy because nothing is necessarily easy for anybody, right? Everything is easy after the fact and nothing is easy before the fact. But this problem, question number 1 of the homework, which you did a long time ago, hopefully wasn't the hardest question on the homework. And I think that with this question, what you might notice is, even if you didn't write all this down that I'm asking you to write down, even if you thought the problem was so easy that you just did it in one line and you didn't drag all this out, and even if you're totally bored, you're like, why is Abraham doing all this? I think you would still agree that if you found this question easy at all, and and then I'm going to multiply, and the answer is going to be like -30 newtons. That's going to be the answer in a minute. Even if you did that in your head, what your head had to do in order to solve it was it first had to say, well, the question was, what is F? So your head had to go, well, F equals -kx. And in this case, K is 200 and X is 0.15. So 200 times 0.15. Like even if this was such a joke that you did it like that, what did you do like that? You said to yourself, well, F equals -kx and K is 200 and X is 0.15. So the answer is going to be 200 times 0.15, right? You had to know that F equals -kx first, and then you had to apply the particular numbers here and multiply them together, right? So you have to know what's true And then you have to apply the truth to make it relevant. Why am I saying this? It seems so obvious, right? Yes, it's obvious when questions are easy. The thing is, when people get to exams, especially in science, when things are hard, when people panic, what they tend to do is the exact opposite. What people do when they, at least what I do and my friends do, and I've noticed after 30 years of teaching, what we tend to do when we, just like when you're drowning in the water and you panic, you do everything wrong, right? Like what you should do is like relax and like float or whatever. But when you're panicking in the water, you start flailing and and then someone tries to help you and you thrash them and you like drown yourself. What people do, okay. What people do, oh, sorry, wait, someone's responding. Wait, let's look at the chat. Wait. Yeah. Right. No, and it totally happens to all of us. And so partly what I'm trying to do here is something a little bit maybe psychological, but yeah, totally, like half of our problems in science are not intellectual, they're psychological, they're like confidence kind of things, right? And what's really weird is that we don't just forget when we panic in exams, we don't just literally forget knowledge, scientific knowledge that we had, we actually forget how to think. And part of the reason that we forget how to think, honestly, is that when the thinking was easy, we never really paid close attention to how the thinking went. When thinking is easy, when thinking is comfortable and relaxed, it proceeds from general truth to particular application. Like literally, if someone were to say, is Socrates mortal? What we do is we say, well, all people are mortal and Socrates is a person, so I guess Socrates is mortal. I mean, that's like a dumb example, but it's a classic example, right? Like that's what you do in your mind, like you, right? But when we're panicking on tests, what people tend to do is they scramble to think of things that are relevant to the question. Like you see a question on a test and you know you studied, so you try to think like, what did I study? What does it have to do? Oh, and you start writing down things that you think have something to do with the question, or to show that you know what the question's about, or to show that you know that you studied. And you I write down things, and then I busily try to contort those things until they sort of become vaguely true and accurate. And that's if I'm lucky. That's if I write anything down. Often I just blank, like Marina just admitted or shared, which I appreciate. But the reason I blank is because I'm so scared that I don't know what the professor's looking for, or I'm like so desperately trying to do what the question is looking for that I start thinking backwards without realizing it. And then that screws me up. What you want to do is just think of things that are true first, and then start applying them to the question, particularly because, or I mean, especially because if we get in the habit of just writing down things that are just true, like even if they're just straight up from an equation sheet that might or might not be given in the exam, if you just write down things that are true, the thing is, they're true. So they're not wrong, they're right. Even so, at least in this class, you're going to get points for writing down something that's true, because how can I take off points if it's right? So what I'm saying is, like, first, we just write down f equals negative kx, because that is just true. Even if I know it's vaguely topical, like the whole problem is about springs. So I write down something that is true about springs. And in this class, at least, I would get points for writing that down because it is f equals negative kx, because it's freaking right about springs. Now that I've written it down, I can start thinking, okay, do I know in this problem what k is? Or what x is? Ideally, I do, so I write them down. If I don't, then at least I now start knowing what it is I have to start thinking about. Oh, I don't know k. That's my issue. I need a k, and I will eventually teach you tips and techniques and tricks for like getting a k if you don't have a k. But I'm saying, the more we panic, the more we tend to try to write down things are relevant and then make them true. And that is ass backwards, excuse the language, but it literally is backwards to write down something that seems relevant and then try to make it true. Because you can't make chicken soup out of chicken shit. I mean, again, pardon the language, right? You can't turn something into a truth that you, just because you hoped it was relevant. What you can do is turn a truth into something relevant. And that's what the mind does automatically when it's relaxed. But It won't do that if it doesn't have the habit of consciously doing that. It needs to develop the habit of recognizing that. So one of the reasons when I'm dragging out this whole procedure, and I know I'm boring some of you, and I apologize. Like I am. Or what some of you might really be thinking is, oh my God, I cannot believe how long he is taking with one freaking question of the homework. And the question was just a simple plug-in. I know I am. And I do apologize. But what I'm really trying to do here is deliberately take a question that we all think, oh, okay, cool. Okay, I appreciate that. Thank you. Okay, I appreciate, good. I'm glad. I mean, I'm a little defensive. Am I a little defensive? Okay, I'm a little lively. No, I do appreciate your appreciation. And I'll tell, and I will move on too. I won't do this forever because I also do know that it still is kind of torturous to some people. But here's what I'm really, really trying to do. I'm going to write this down in the next thing. Like, no. What just happened? Oh my God. Hold on. I know it's gone. Wait. Okay. What about the board? I don't know why the board keeps doing. Okay. So what this says here, note number 2, I'm just commenting on like why we're doing all this. Okay. Is literally what I'm actually trying to do is it says the 5-step method is designed to take a mental movie of what our mind does when it operates quickly and slow down that movie so that we have something to watch during hard times. Like I mean, that's like a weird thing to say, but I'm saying like, I know you know how to do this question. And I know that I think that, F equals negative KX, like what's F? I mean, K equals 200, X equals 0.15. Oh God, and there goes my board again. Talk about hard times, talk about stress. Let's talk about stress. Let's have group therapy. Oh wait, we already are. Okay. I'm saying, boom, come on. Okay. I'm saying that if we take a question that's semi-straightforward, like K equals 200, X equals 0.15, what's F? I'm sure that most of you don't need to do all this in order to do that question. Like I totally get that. And that's also why I'm not taking off points or anything on like this first homework. I didn't expect you to do all this, and I'm not grading according to all this on the first homework. Like you do what you do and you do it your way, and it's fine on the first homework. What I'm trying to say now that we've done most of us have done at least the first question on the first homework, I'm trying to step back and say, you know what, if you did that first question super quick and it wasn't like that hard, let's like actually take a movie of what went on in your mind when you did it. Let's take a movie of what went on in your mind when you didn't need any help. And let's like slow down that movie and look at what you did when you didn't need any help. Because actually, when you need help, the help can come in the form of watching that movie. Like notice that when you think you know stuff, even in a quick beat, it's not one beat. It's a bunch of beats that move really fast for you when it's easy. right? In order to know, to just plug in and know that the answer here is going to be negative 30 newtons, you first had to reference the fact that F equals negative kx. Then you had to reference the fact that K is 200 and X equals 0.15. Then you put those two things together, and you'll get negative 30. So whenever you get to a question in the future that's a little bit harder, what I'm saying is then realize that this is what you actually had to do. You had to draw a diagram, really, even if it was in your mind. You had to know what the question was, even if it was in your mind. And when the question's hard, it's better for it not to just be in your mind. It's better to be on paper, especially so you can see what's making the question hard. And then after you write down the question on paper, it's really good before you start solving to write down the truth that's going to generate the solution. Then start applying that truth to the particular question, right? And this means there's 3 things you can always do, even when you think you have no idea. When you think you have no idea, there's at least 3 things that you can do and should do and will get full points for that will actually show you that you don't have no idea, you have some idea. And you're missing some idea. And by writing these 3 things down, you'll pretty much, or these 4 now, you'll know what idea it is that you think you were missing, if you're still missing it at all by the 4th step. Honestly. So number 1, we're going from true to relevant rather than relevant to true. Number 2, we're going to, and I'm sorry. So therefore also the reason that I'm from here on in going to ask you to do all this, even for easy questions. I'm going to ask you to do all this, even for easy questions. First of all, because you get all the points. But second of all, because this crap doesn't work on hard questions unless you've practiced it first on easy questions. So get in the habit of doing all these steps, right? And notice that you're getting all of these points without even having any kind of correct answer or any kind of, you don't have to have anything correct to do this, to get all these points. But then finally, sorry, just comment note number 3. One of the reasons we freeze in exams, and I say we, I am not saying you, believe me, I'm including myself first and foremost. But when I used to freeze in exams, first of all, it's usually because I felt I had no idea what the question was asking, and it totally bummed me out. But second of all, it would be because they would say things like, show all your work, right? And I'd be like, oh, great. Like, it wasn't hard enough that I have to get a right answer, which I'm like totally having no clue how to do. It's not good. It's not bad enough that I have to get a right answer, but now I have to justify all my reasoning. Like, even if I vaguely remember how to do this from last night, it's not good enough to vaguely remember how to do it. I have to show all my reasoning. So I'm going to lose all these points for not showing my work. That is so unfair and so annoying. Like, can't I just give you what I got? But so then I'd freeze up more. Here's the thing though, showing all work, it sounds like an extra burden. It sounds like this extra, it sounds like we're saying, and maybe some professors are, when we say show all work, it sounds like we're saying now prove that you actually understand where you got that answer, prove that you didn't cheat, or copy that answer off the soul of the girl sitting next to you or something, right? But that's not, and maybe some people do mean that, but that's not what I mean. When I say show all work, or when I say you have to do this whole step method, I'm looking at the chat. I see something in the chat. No, right, it does. Showing all work does have high standards in certain classes. And honestly, I don't really mean to make light of it, and I don't want to deceive you. I'm a big believer in showing all work. But again, this is one of these things that ends up getting twisted backwards. When we say show all work and we put this big emphasis on it, it sounds like we're saying you're going to get punished if you don't justify how you knew what you knew. And that's actually not meant to be the point. That loses the whole, what we're trying to say or should be saying is, hey, you know what? You may have a hard time getting to the answer. Our questions in physics are hard enough that you may not immediately understand the question or let alone see a path to get to the answer to the question. But if we show you a method for doing the work that you need to do to get you to understand the question and the answer, if you show your work, it will help you get there. It will help you unfreeze and unpanic yourself. So what I'm really saying specifically is this. When I used to ever hear the phrase show all work, what I thought that meant is show all my computations. Which it partly does. So I would immediately start diving in and start like grinding computations or panicking into computations or stressing computations, but they would get stressful and often wrong or messy, or I'd freeze up. But part of the reason was computations don't work if you start with computations. The work, anytime anybody says show all work, what most of us, including me, always think of is all this stuff of step 4. And unless I totally know what I'm doing right from the get-go, step 4 collapses on itself. It falls apart. It becomes a stress mess and a big bunch of mistakes, if you're lucky, or it becomes nothingness if I start with step 4, which is what most people accidentally or nervously or unconsciously do on exams. They just start trying to do computations that look reasonable. But I'm saying what most physicists do is spend most of their time setting up computations. The setup is the key. And if you break up the setup into tiny steps, then you always know what to do before you're even doing it. Wait, I'm just looking at the chat. Okay, yeah. So, I mean, basically what I'm really saying is, if an exam is a meal that you're supposed to eat, you actually really want to set the table first. And no one ever wants to do that when it seems easy, because that seems like a waste of time. Like if you just know in your head, well, duh, f equals negative kx, let me just multiply the k by the x. Okay, blah. Then it seems like a real waste of time to draw a whole big diagram and write out what is f and write out k equals. It seems like a complete waste of time to do all that when you already know what to do. But the thing is, when you don't know what to do, then you won't know what to do. So when you do know what to do, you should do all these steps. You should spend 3 steps before you even freaking do a computation. And then that way, when you don't know how to do your computations, you'll have it in your muscle memory that the way to do computations that you don't know what to do, that you don't know how to do, is to spend time setting them up first with step 1, step 2, and step 3. I'm saying that bottom line, I'm saying whenever we've ever heard the phrase show all work, what we're all instinctively automatically thinking is the step 4 stuff. And we're skipping straight to that. I'm saying step 4 is step 4. Like do steps 1 through 3 first and do them, especially when they seem unnecessary, because then they will work when they're necessary. And yeah, so that's what I'm saying. So, okay. So that's step 4. And then finally, step 5. So yeah, step 4 is where all the action is for. Oh, and in step 4, you should. Sorry. Back. I have to make a comment too. Last comment. All right, step 4 is a bunch of equations that get simpler and simpler as they go, or get more and more filled in as they go. But step 4 is a bunch of equations, not fragments, not references, equations. An equation is a complete thought. This is the same thing as that, right? So that's step 4. So step 4 is the meat for sure. Step 4 is the work. Step 4 is usually the long part, but step 4 is a lot shorter and easier and tighter if you've first done steps 1 through 3. So then step 5 is FAC as in facts, yo. But what I mean by FAC is final answer circled, as dumb as that sounds, but it's not dumb. So so in this case, so step 5 is FAC, and that's where we end. Step 5 is FAC, final answer circled. So for this particular problem, and obviously I'm going to speed up I'm looking at the time. Okay, I'm going to do the next, I'm going to get faster and faster with the questions. But for step 5 here, we had just written, so here. We had just, said F equals negative 200 newtons per meter times 0.15 meters. And we had just canceled out the meter units. So we get F equals, F equals negative 30 newtons at X. Okay. Actually, wait, okay, I'm going to do this again. Sorry, I'm getting too crowded. I'll write that on the next sheet. Hold on. So, okay, I'm going to make some comments about this. First of all, okay, so we've now done one question out of our first homework. I do believe that's the answer. I believe the answer is force equals -3. The force exerted by the spring on the mass at that initial displacement, I believe, is -30 newtons. I'm assuming that to the right, I mean, okay, tell me if you want me to, I'm going to go back to that page in a second. I just want to say, going back to the diagram for a second. Okay, so here's my original diagram, right? One thing that I really should have put in my original diagram is, let's make it clear that this direction is positive and this direction is negative. Now, that's a choice. that's a choice, but I think that is the choice being made by the original problem, because it says that the block is originally pulled out to a displacement of 0.15 meters, not negative 0.15 meters, but positive 0.15 meters. So this place where the mass is originally held is apparently the positive side of equilibrium, and the other side is the negative side of equilibrium, right? So the displacement is positive, but the force exerted by the spring is always trying to bring us back to equilibrium. It's always oppositely directed toward that. So, like, in other words, F equals negative K times X. So the original displacement was positive 15 centimeters. The force exerted by the spring is negative 30 newtons. Negative 30 newtons. And that is our final answer. So I'm just saying right now that in the diagram, I said the whole purpose of the diagram is to label and define a bunch of things. One of the things that should be labeled and defined is your coordinate axes. But going back to the, oh, there goes the board again. Okay, so going back to, sorry, Ashton, you have your, oh God, I don't know how long you've had your hand up. I'm sorry. Yes, Ashton.
Literally a second, you're fine.
Oh, okay.
So I'm just thinking about, because obviously I did this with Walters. I'm gonna blank on what it's called, but do we need to put, like, I think they're called like points of like relativity, like, you know, one way is positive, one way is negative. Like, do you want us to put that in the diagrams? Because I used to put that in her class. I just don't know if it's needed here.
Yeah, no, that's awesome. I'm totally psyched to hear that. Yes, please. It's my bad that I didn't make that explicit right at the beginning of this problem. Yes, that's definitely something that really should be, and there goes my board, in the original diagram. Yes. And so that's a great question. And you just wait, I just had a panic attack. No, I didn't, but you're right. You're reminding me, I forgot. You had Walters. That's awesome. But that's unusual, right? Most people in this room had,
Yeah.
Right.
Because I
Okay.
changed my major, but it's no big deal.
Okay, no, that's great. No, I mean, good. Wait, okay, well, that's a discussion for later. Okay. But so you did the 5-step method with Walters, in other
Yes,
words?
I did.
Oh, right. Okay. Which is great. I'm glad. And that reminds me but am I right? I just hope I'm not, but everybody else in the room, you guys have not seen this 5-step thing before. Is that correct?
No, I haven't.
Okay, good. I mean, good in the sense that I'm not wasting. Okay, good. Right. Okay. I forgot that Ashton had, but right. Okay. So yes. And Kayla's on fire with the participation, I have to say. This that's awesome. Oh wait, and Ariana, right. Okay, I'm just looking. Yes, okay, all right. Cool. In the closed kit. Oh, and neither have I. Okay. Oh, thank you. Direct chat person. I will not mention your name, but I totally appreciate that. I mean, I appreciate that input. Okay, good. So this is not I have found over time that it's not taught in every class, clearly, but I think the thing about this method is I'm telling you guys that I will explicitly reward your use of this method. I will explicitly grade according to this method. Like, it's explicit. It's like a rubric for points as much as it is, a strategy for solving. But I will tell you from my experience, even in classes where they're not explicitly using these acronyms or whatever, what I have found is that really this will help a lot. If you do this, if you break down hard quantitative science problems this way, and you'll see, we're going to just do it this way from now on all problems. I'll be much faster. Don't get me wrong. I'm not going to talk all the way through all of this every single time, but I'm going to do these steps every single time. And you will find over time, if you use this method for solving problems, particularly when they're hard, particularly when you think you have no idea when you're starting, you'll find even that you'll get much more points on the problems for doing this, even if the professor doesn't consciously know these acronyms. Honestly, it's a way of, again, the whole point of this whole thing, and I think I put this sheet, I think I have a sheet on this that I put in your classroom, and if I didn't, I will. This whole thing is about knowing what to do when you don't know what to do, which is really If you really think about it, that's the secret we're all looking for all the time as we're trying to advance in our career as science researchers. Like, I mean, we all know this, right? Like, first of all, we hate the feeling of not knowing what to do. And it happens all the time in science. Second of all, if we're really trying to go on in scientific research, that means we're literally signing up for a situation where we're going to do original thinking, where there really isn't a roadmap. Like, right? If you really want to like do stuff, that means there isn't an algorithm for what you're doing. So what the heck? Like, how does that ever work? How does anybody ever think themselves out of a box for which there's no thinking map? And the answer is this. I mean, not literally only this, like there's other ways too, but there's got to be a technique for getting ourselves to the end of a tunnel where we don't see the light. And part of the real secret is taking is starting to walk in some direction, right? Like, okay, last sidebar on this, and we'll go back to, but the other reason that you might have noticed that you guys, like science people, you might notice that you tend to have breakdowns and meltdown. Okay, I don't want to speak for you, but some of us as science students and science faculty, like break down and panic every once in a while. And we don't necessarily see our friends in other majors doing that as much. I don't know, call me crazy. One of the reasons sure is that science is hard, like duh. But you know, the other secret reason is that you wouldn't be here if you weren't used to success at a certain high level in your past endeavors. And the problem with success is that we start getting used to it. And it starts becoming, and the more success you practice, the less you practice frustration and failure and challenge. So, or put a really rude way, the smarter and smarter that we get, and the more and more we practice being smart, the less we remember how to deal with feeling stupid. And what becomes really problematic as a science student is every time something comes up that we don't actually know or we don't feel good about, it's really upsetting because we don't like that. Like, we didn't get here for having screwed up. We got here for having done well. So then when we screw up, we think, or when we feel like we're screwing up, it feels like a big screw up. Oh, okay. Okay, I'm so psyched that Remy. Okay, cool. Wait, I don't even know what FR. Wait, I think I know what FR means. I'm not sure, but okay, cool. I mean, I'm glad I'm related. Okay, so yeah, like it's real. So honestly, part of what this whole method is a method for reminding ourselves like what to do when we feel a little bit stupid, because we need, because when science is actually happening, science class and stuff, it makes smart people feel stupid all the time. Like the smarter the stuff, right? I mean, right? So we need to know what to do when we don't know what to do. And this is what to do. But the only way to know what to do when we don't know what to do is to practice doing things that are what you have to do when you don't know what to do, to practice them when you do know what to do. So you see how they work out, right? Okay, anyway, so the answer to the first one, but I'm glad Remy said that. The answer, oh, wait, God, was that direct chat or? No, it was public. Okay, phew. All right, so the answer to the first one is F equals negative 30 newtons. That's the answer. Now I'm going to start trucking. I'm going to keep doing this method, but I'm not going to keep explaining it, right? I'm just going to like do the method for the next questions. But I will show you when the method is kicking in at a deeper level. Like I will point that out every time. But again, you get points for, so from here on in, you notice you can't even lose points for a wrong answer until you get to the fifth step. Until that point, it doesn't even matter what you think the answer is or not. It only matters in the fifth step. Oh, and so a couple more comments on the fifth step. Sorry, almost forgot. Here we go. Wait. Oh, there goes my board again. Right. Oh. Oh, thank you, direct chat person. Oh, FR means okay, cool. Thank you. I'm so dumb that I didn't realize that. Okay. I thank you, direct chat person, for explaining FR. I actually thought it meant fucking right. Okay, sorry, I didn't say that, but for real. Okay, got you. Thank you. I should be embarrassed enough to have kept to myself that I didn't know, but I didn't. So thank you. Okay. That's totally points for participation, direct chat person who just told me that. Okay, so notice, first of all, the final answer, which is now circled and highlight, right, refers back to the original question, which I mean, that seems dumb and obvious, but people don't do it. So you want an answer that actually answers your question. You want to close the loop, right? And that means specifically, that this is really important when I'm writing here. Like, okay, so the original question was at x naught equals, at x equals x naught, at x naught is 0.15 meters. What is F, right? That was the original question, which we made clear in step 2. Then in step 5, at the end, we wrote an answer which literally said, at x naught equals 0.15 meters, F, the force, equals negative 30 newtons. Now, right, so first of all, it showed we knew the question, we knew when we knew where the plane was supposed to go, and we knew when we landed the plane, right? And we circled our final answer, which is like really important. Actually, again, it sounds like 7th grade, but it's really important to make it clear to your reader that you know when you've concluded the scientific conclusion that you're trying to come to. But now let's be more specific about this. That answer that we circled in the end actually matches the question in terms of its details. Like the original question was asking for a force. Oh, yes. Wait, I think, does that mean go back? Oh, yeah, absolutely. Great, thank you. By the way, again, and that's Kayla. Thank you for going public. Can I just also point out that what Kayla, I think, if I'm understanding, she just asked me to like go back in the slides. I believe you'll find, I don't know if I told you this last time, there's new portals for that. There's literally a portal for asking me to go back a slide. You get points for asking me to go back because like totally shows that you care and you're paying attention and it helps me teach you better. And there's equally a portal for telling me to speed up and go faster because I'm like boring the crap out of you, or I've already said the same thing 17 times or whatever. There are portals for this. Like Kayla should submit for points for the fact that she just asked me to turn back a slide. And if anybody in the direct chat wants to go like, okay, we get the point, Yaverbound, we got the point. Can you please move on? I mean, if they asked it in a polite way, they could submit that for the portal that says going forward, please, or something like that. Okay, just no. All right. So yeah. Okay, no, fair enough. No, absolutely. So all right, so that was so that's note 1. It refers back to the original question. Now what I'm saying in note 2 is that they match in terms of details, such as units. Like the original question asked for a force. So your final answer was force equals negative 30 newtons. Now, here's another twist. I know I'm dragging this out, but I'm going to, give a person a fish and they eat a meal, but teach a person to fish and they mix metaphors forever. You know what I'm saying? What I'm saying is, what am I saying? I'm saying, if you interpret this one way, I'm giving you tons and tons of requirements that you have to follow in order to get points. Like, yes, I'm saying if you're asked for a force and you write down what is the force, then by the time you get to the step 5, I am saying you better give me an answer that literally has units of force, i.e. newtons. You could interpret what I'm saying to be like extra requirements that make it harder for you to get points and harder for you to succeed in life. But actually, if you look at it in a different light, what I'm actually saying is, no, these are tricks of the trade. What I'm saying is, let's say it's a hard question and you don't know what the right answer is at the end, or you put an answer down, but you're not sure if it's right and you're really worried you're going to lose a lot of points or blah, blah, blah. Or let's say you literally have no clue what the last final answer is and you're really afraid you're going to lose a lot of points. I'm saying, well, you know what? For starters, if you wrote down the question, if you felt you knew that the question was asking for a force, a big favor you could do for yourself is you could write down a bunch of stuff. And then by the time you get to step 5, you could at least write F equals blank newtons. You could leave it blank and write newtons, or you could write down a number that you may or may not think is right. Or you could even say F equals F naught newtons. Like you could make up a symbol for it. What I'm saying is, if you even understand that what you're looking for is newtons, you've actually helped yourself a lot. With me, explicitly, you'll get points. If you even just write F equals newtons, you're showing me that you totally get the kind of answer that you're trying to look for. And honestly, if you know what kind of answer you're looking for, you're already halfway there to the correct answer. You're going to get a lot of explicit points from me. And I'm telling you that even from professors or even in contexts where they don't think they're being explicit about this, you're going to make a lot of headway. So you're just fitting a puzzle together. Once you know what the actual question is, you know what the final answer has to look like. And if you even show the reader that you know what the final answer, what format it should take, you're much closer to answering than you probably think. So use that as a standard to match up your final answer with your original question. And then also yeah. Okay, here's the ultimate goal of this whole thing. Whether the question is easy or the question is hard, your goal by the end of the 5-step method in solving any problem, short or long, if you solve a physics problem with the 5-step method, then by the end, you will have provided and I can go back to the slide in a second if you want. Okay, this is the ultimate standard. I'll read this out. I'm going to still go to the next page. I know this is all getting crowded. Hold on. This is the ultimate standard. I'm saying the real purpose of this 5-step method, it's really, well, there's two purposes, whatever, is that if you do if you do the work out according to the 5-step method, then if you do it right, this is how you know if you've done it right. If you do it right, I don't even mean if you got the right answer. You might not get the right answer. And part of the whole thing about this is even if you don't get the right answer, you're going to get a ton of points, a ton. If you do the process correctly. What do I mean by doing it correctly? I mean this. You will have produced a solution that stands self-sufficiently on its own. A solution, in other words, that a derivation that could be followed, read, understood independently by somebody who knows physics, or whatever the subject material is. I mean, in this case, it's physics. Someone who knows physics, even if they do not know the original assignment. In other words, right? If you do this correctly, like in a blue book, someone could read the blue book without even looking at the test booklet and follow, because you've done all this, you've done the diagram, you've done the question out, you've done the principles, you've done the work, and then you circle the final answer that leads back to the question. If you actually do this correctly, that means someone could just look at your blue book, not have any idea what's in the test booklet, and just follow along and be like, oh, that's good physics. Oh, that's interesting physics. Oh, that's right physics. Oh, I just learned some physics from that, right? If you do this right, someone could follow along, which means two big things. I.e., if you do this correctly, whether the question was easy or hard, if you do the method, then you've taken the reader, whoever's grading your homework, whatever, or your exam, you've taken the reader from a question to an answer, that all of which is contained in your work, and you've shown them how to solve a particular problem from question to answer, which means that what was originally some just dumb assignment that some like long-haired, freakish professor annoyingly gave you to do, you've turned that dumb, arbitrary, particular John Jay assignment into an actual proof that stands like a piece of physics on its own, right? Like even this first question we just did, I'm not saying it's fascinating, but if we did it out according to the method, then what was Yaverbaum's sheet number 1 is now, how to find the force exerted by a mass exerted on a mass by a spring, right? Like given these things, if you have a spring with these conditions, this is how to find the force exerted by the spring on this mass. Is it the most fascinating thing ever? No, but it is itself a little physics proof. It is a self-sufficient, independently legitimate little physics proof or discovery or procedure that could be now used by anybody else who reads it, right? Like, I'm not saying it's fascinating, but it's legitimate. It was just Yaverbaum's assignment, but now it's how to find the spring force exerted on a mass in general, right? What does that mean? That means if you do that, that's the standard. You want to turn stupid little Yaverbaum assignments into actual pieces of legitimate physics. And if you do that, why is that a good thing? For 2 reasons. And then we're done with all my yelling. Well, with this yelling, that means 1, Okay, I don't know which one of these two things is more important to you, but but I'll say them and then we're going to move on. And I don't mean this lightly at all. Oh, I see. So wait, there's something's in the chat. Wait, or did I already get it? Interesting. Oh, the Remy thing, interesting. Fair enough, because I am going. Wait, the question 7. Wait, 7. Which one's 7? Maybe. Let me think about that for a second. Certainly a legitimate question. Remy, but and I'm also just thinking. Okay, sorry. I know time is flying. Just what bottom line with this. If you practice this method, what you're really doing secretly is turning stupid homework assignments into, you're turning every stupid homework assignment into that much more practice for publications and presentations. Like what you're doing is you're turning your work into something that any reader could actually get something out of, even if they're not sitting in your same context. And that's what scientific research and publication and jobs and stuff are really all about. The whole point of science is that we're trying to communicate findings and results that we get to an audience that isn't necessarily sitting in the same lab as we are. We're trying to communicate outside the limited context that we came from. So the real point of this method is to take any stupid little problem that one stupid little professor, whatever, gave you, and actually turn it into a scientific finding that actually would be readable and followable by anybody. That's number one. So if you care about going on in science, that's really what I'm trying to. And I'll tell you one of the biggest steps to that is that stupid step 2. What is the question? I cannot even tell you. I won't, out of respect for Remy and other people, I won't go down a whole side road about how the huge number of stories I have from graduate school where genius documents that were hundreds and hundreds of pages being offered by PhD students in this and that, but the documents did not land at all, or fell apart, because for all of the information that was being provided in this document, it was never at all clear what question the person was trying to answer. Like the key thing, so just an example, like actually taking the moment to say, here's my question, and here's my work, and here's my answer to my question, is so the key to science. I can't even emphasize enough. That's number one. But number 2, just on a really concrete level, and hopefully this will get me to sort of addressing Remy's thing, is like, honestly, what I'm really getting at here is when you do your homework and you do exams, you want to produce a document that takes as little effort as possible for the professor to give you as much points as possible. And the way to do that is to create a document that doesn't require any cross-referencing. Your ideal in any exam solution or any homework solution is to give me something where I don't have to look at anything besides what you've given me for me to see that it is really smart, tight, coherent, correct physics. That's really the goal here, is to create a document that requires very little effort for the reader to be like, whoa, right? That's the point of the method too, to give. So, all right, I've said enough about that. Let me, okay, here's what I'm going to do. I know what I'm going to do. As a compromise for the moment, we're going to keep doing this in layers. As a compromise, like between what I'm trying to do and what Remy's asking, because it's fair, because I know I'm taking so long. What I'm going to do now is I'm going to quietly, first, I'm going to write the answers to a bunch of questions on the homework, so that, because I know I've taken so long with this. So first, right now, I'm going to write out so I'm not writing out the solutions. Right now, I'm just going to quietly write out the answers to the rest, or to a lot of them, so you can at least see if you've done it right or wrong, and we can see where we have questions. And then I'll probably, maybe not today, back up and start slowly doing better solutions, or wherever you have questions. But okay, I think that's a compromise. I'm just going to wait. So I'm going to write answers. These are not solutions, but just so we can make some headway here, okay? And then maybe at question 7 or something, I'll pause and we'll do solutions. But I can't see your faces right now because I'm looking at the screen. I'm looking at
that sounds perfect.
Oh, okay, great. Okay, thank you. I appreciate the feedback very much. Okay, great. And thank you, Kayla. All right, awesome. Here we go. And I'm not going to redo the diagram. I'm going to assume you have the diagram. I have to look up what the question 6 is. I think I know. Hold on, sorry. I don't remember what the question is.
In meters, how far will the mass compress the spring?
Oh, yes, thank you very much. Awesome. Thank you. I appreciate you guys really are paying attention. Thank you. Yes. Okay. Okay. I'm going to pause for a second so people. So actually, yeah, you're right. Question 7 is probably about where we should. Okay. I'm just gonna. In fact, I'm going to. Okay, I'm looking at the time. And again,
if possible as well.
Oh, sorry. What?
Oh, I said, since you started 4 and 5, if possible, can you go over those 2 as well later?
Yeah. Can I later go over question 4 and 5? Is that what you just said?
Correct.
Yes, absolutely. In fact, I was just going to say yes, absolutely. I'm almost tempted to do it now, but you're right. Yeah, I'm going to layer this. Yes, I definitely am. Here, I'm going to make some. Here's what I'm going to say for right now. Now, again, to everybody, I'm conscious. I totally think this is legitimate. Like, I think it's long overdue that I do this. I think just as long as it's clear to everybody, this is not an example of the 5-step method I'm doing right now. I'm just trying to like be practical right now, but just as long as that's clear. Okay, so for questions 1 through 3. Oops, sorry. Well, yeah. Okay, what I'm doing right now is, well, what I'm doing right now, sort of trying to peel this onion, I'm saying the the diagram is the same for every single question. And by the way, say this were an exam and I'm asking you to do the 5-step method on an exam. On each next question, since it's the same diagram, you can write like step 1, C diagram above. I'm not like, you can always say C diagram above. You don't have to draw the same diagram a million times. Okay. But then step 2 for each one would be what the question is. You guys can see what the question's on your sheet. So one thing I'm trying to do right now, just to make progress with us, is I'm telling you that for questions 1 through 3, the GDPs are F equals negative KX, i.e. Hooke's law, and Newton's second law, F equals MA. Like those are the two statements that I used to solve questions 1 through 3. I have a slight suspicion that most of you probably, or actually I think I remember, most of you probably got questions 1 through 3 correct or can see how I did it. I used F equals negative KX and F equals MA. We could still go, there's still things to say about that, but I have a feeling you're okay with that. Then for the questions 4 through 7, where we are going to have to talk a lot, we are going to go back and talk a lot over the next couple of weeks. What I'm using there is the conservation of total mechanical energy. Now, there is a lot to say about that, but the summary is like the GDP for questions 4, 5, 6, and 7 is, I'm saying when all the forces doing work on some system are conservative forces, when all the forces doing work on a system are conservative forces, then the system will conserve total mechanical energy. The total amount of mechanical energy at any one place will be the same as the total mechanical energy at any other place. Now, for some of you, that's totally clear. For some of you, that's like not at all clear. I understand that. I'm giving you broad strokes here. The broad stroke is that when all the forces doing work are conservative, total mechanical energy is conserved. Now, over time, I'm going to define more specifically for all of you what I mean by work, what I mean by a conservative force, and what I mean by total mechanical energy. But I will tell you, especially if you got some help from the web or you remember certain things from Physics 101 or whatever, I will tell you that how that translates into an equation for this sheet, for this context, is the 1/2 mv squared plus the 1/2 kx squared of this system at any one spot has to equal the 1/2 mv squared plus 1/2 kx squared at any other spot. I will explain that further. For some of you, that'll be a reminder. For some, but it's true. The truth is the sum, 1/2 mv squared is what we call kinetic energy. Always. The 1/2 kx squared is for a spring, what we call the potential energy. Like different forces have different potential energies associated with them. For a spring, the potential energy is 1/2 kx squared. Again, I will explain that. But I am saying right now that if you look at any one spot in this situation, if you look at the mass over here and you take all of its kinetic energy, it's 1/2 of its mass times the speed squared that it has over here. And over here, the speed is 0. So it has no kinetic energy at all over here at the beginning of the problem. And you add up all of its kinetic energy with all of its potential energy, all of the energy that the spring is storing, which is 1/2 the stiffness of the spring times the square of the display. In other words, 1/2 times 200 newtons per meter times 0.15 squared. If you add all that up, that's the total amount of energy that the mass has over here. Over here at the beginning, it doesn't have any kinetic because it's not moving yet at all, but it's storing all this energy from the spring, 1/2 kx squared. That total amount of energy, once you let the mass go, is just going to get converted slowly as it's moving to a different form. Like all of the potential energy it has here will get progressively more and more turned into kinetic energy to the point where it gets all the way here to equilibrium. All of its energy will now be kinetic. It will have no potential. And you look at the equations, like it'll have a whole bunch of motion, V, but it won't have any X. X is 0 now. It's sitting in equilibrium. So what I'm saying is the total amount of energy, all of its kinetic plus potential over here, has to be the same as all of its energy, kinetic plus potential over here. It's just that at the beginning, it's all kinetic, it's all potential. And progressively, that's all going to turn into kinetic. So the thing that you're solving for, so I guess in a way, I'm sort of skipping to question 4 right now. I'm giving a broad overview of question 4. I'm saying what you're solving for is V at position X equals 0, But every other one of these terms, you know V at the beginning, it's 0. You know X at the beginning, it's 0.15. You know X at the end, it's 0. V at the end is what you're solving for. Okay, and that statement, again, I'm going to back up and say that in more detail like soon, but that statement that the total amount of energy over here must equal the total amount of energy over here, it's just that we're converting from potential to kinetic as we go. That statement is also literally what you would use in question 5. In fact, yeah, you use that statement in question 4, you literally use it in question 5. It's just in question 5. In question 5, you're solving for X instead of solving for V. So you're solving for something different, but it's the exact same statement. And honestly, even in question 6, which is when it says, how far will it go to the other side until it stops temporarily and starts coming back again? You're even using that equation again in question 6. In question 6, it's asking, when's the next time V is going to be 0? So again, what you know is that at the beginning, V is 0 here when X is 0.15, and you're looking for the next time that V equals 0. You're solving for the other X. Well, if you think about it that way, if on the left side of this equation, V is 0 and X equals 0.15 squared, well, if you're solving for where on the other side V is 0 again, the only way that the two numbers are going to work out again the same way is if you do negative 0.15 squared, which is the same thing as 0.15 squared. I know I'm saying all this a little bit quickly now, again, just to sort of compromise and get us back on track, but I'm saying that the GDP that you would use for questions 4, 5, and 6 is the same GDP. It's energy conservation. That's a big enough deal that I need to say more about it, but that is what you use for 4, 5, and 6, and even 7. Even question 7 says, question 7 to the, well, so question 7 to get up to where Remy's asking. I believe question 7 was how many trips does it make, right? Until it eventually, right? Right. Okay. And the answer is, if this is all true, if we're believing the math that we've been doing for the first 6 questions, or put another way, if we're believing that energy is conserved.
Professor, can I interrupt you?
Oh, sorry. Yeah.
After this, would it be possible to do like 5 or 4, like through hand? Because I messed up somewhere and I don't know where.
Yes. I think that's a great, yes. Hang on one second. Yes. I appreciate that. Wait. Yes. Okay. So I'll just say this statement, and then when we do question 4 and 5, we're going to do the math of energy conservation, and it will look very mathematical, and we'll get a number. And I'll do it in 1 second, hopefully, I think. But if we believe that math, then we got to believe it. If we're using that math, then we believe that energy is conserved. That means we believe that the mass is only ever converting from kinetic to potential and back and forth. It's never gaining a net amount of energy or losing it. So that means there's no reason. That means that if it's going to start at 0.15 on this side and go to negative 0.15 on the other side, then by that same logic, it's going to come back to 0.15 on this side and go back to negative 0.15 on the other side. There's no reason for this thing to ever stop or slow down or make a shorter and shorter cycle as long as we really believe energy is fully conserved. Now, in the lab, of course, in a realistic spring, it turns out that it doesn't perfectly conserve energy. There's friction on it that eventually starts taking energy away. But if in this theoretical problem, we're believing that energy is conserved, then the answer is an infinite number of cycles. It would be the answer to question 7. Now, I do want to do what Remy's saying. Let me just think for a second. Hold on. Yeah. Let me just think for. Yeah, I think this is a good time to pause. I think it probably would be good. And it's not all about Remy, obviously, but I do think Remy is speaking for not just himself. I think he's probably right that, I just did 4 and 5 like very fast, and there's a lot to be said there. So I think it is perhaps worth it for me now to go back and do 4 a little bit more slowly. Although let me ask Remy, you're talking about the math, right? You want to see the math of the equation that I just wrote and see where you went wrong. Is that correct?
Correct. I plugged everything in and simplified. I got a different answer. So I messed up somewhere, but I don't know where.
Okay, fair enough. Yeah, that I can do. All right, no, that's fair. And hopefully this is helping other people too. And if anybody, I think that is worth doing again, because I know we've been sort of waiting weeks for this. And it's all important for us to all know where we are with this work. So I think this is fair and worth it, and I'm going to do that. But again, people, it's not, you could put in the private chat if you have other desires and even if I can't get to them now, I'll get, again, like I partly want to do all this because I said 2 weeks ago I was going to. So if you have something, you can ask me too, and I'll get to it next week, whatever. Okay, let me just prepare but I'm watching the clock. Okay, so let's. Yeah, okay. So I'm going to pretend, so I'm slowing down a little bit now. I'm pretending that I'm actually doing this like for homework or whatever. So just so it's clear to everybody. Okay. So we're doing question 4. Oh. Okay, I'm going to look in the chat in 1 second. Sorry. Okay. Wait, oh yeah. Okay. Wait. So okay. I'm going to continue with this. No, great question, Kayla. I am actually saying from here on in. From here on in. Yes, please, yes, for homework and exams. But yes, homework. Please do the 5-step method, which means yes, please do it. It means ideally, even as you do each step, at least for now, even just label like this is step 1, this is step 2. Ultimately, on exams, you might not have to label that, but yes, please, on homework from now on, like you're not losing any points. I just taught it to you, so I'm not expecting that you did it before this, but yes, please do the method for homeworks and exams going forward. Yes. I mean, thank you for asking, but yes. And I will keep, when I go over things, generally I'll go over them that way so that you can see, like I'm doing now, like, yeah, I kind of skipped a couple questions, but question 4, here's step 1, the diagram. Here's step 2, the actual question. Here's step 3, the GDP. And notice it's first in English. Total mechanical energy is conserved. That's an English truth. That's a principle. That's a law. But now continuing, like step 3, GDP continued. what that means to say that total mechanical energy is conserved, like it means that the total amount of energy at one position must equal the total amount of energy at another position. Okay, that's what that means. That's a GDP. Well, what does that mean? What's total mechanical energy is all of the kinetic plus all of the potential energy at any one position must equal all of the kinetic plus all of the potential at any other position. That is a GDP. Like that is true. It's not specific to these numbers. It's not specific to these problems. It's just true that when total mechanical energy is conserved, what we mean by that, the definition of total mechanical energy is the sum of all kinetic energy and all potential energy. So I'm saying as a truth, all the kinetic plus all the potential over here at this spot must equal all the kinetic plus all the potential over here at this spot. Okay, that's now. I'm going. Wait. Hold on. Yes. So a great question, also, Kayla. Right. So from here on in, if you want to submit revisions or resubmissions for any homeworks, old or new, yes, to get more points, it would be super helpful. And no, that's cool. No, I mean it's a class. No, I appreciate it. But yes, good questions. I mean, I'm assuming I'm answering them. So yes. So again, I'm totally not at all punishing anybody retro for not. Oh, right. Cool. Oh, good. Who was your physics professor last? Sorry. And I will get back. This will be the last thing we'll do, but I will finish this problem, Remy and everybody else. And then somehow we're going to talk. I know we also have a lab. But wait, sorry, Nicole, I forget. Did you go to John Jay? Who was your physics professor? Or was it?
No, Bronsky College. It was.
Okay, great. Okay. So cool. So you're familiar with it. So good. So I'm not the only crazy one. All right, cool. All right. So all the kinetic plus all the potential. That's my GDP. Now I'm going to start PAW. I'm going to start actually, like the thing that Remy's asking, I'm going to start actually applying to this problem. So in this problem, kinetic energy is 1F mv squared. The truth is, that's always, we could also, that's also it's always true that kinetic energy, it's always true in this level of physics, that kinetic energy equals 1F mv squared. So you could put that also as a GDP if you want, like kinetic energy is always 1F mv squared. But the potential energy here, like, okay, in fact, let me really quickly. What I'm saying is kinetic energy is always 1F mv squared. And by the way, I'm just saying that right now. I think many of you have seen that in Physics 101. There's going to be a point where I go back and re-explain or explain why that is. So right now, in the interest of time, because I think you've seen it, I'm saying it, but I'm not expecting that you necessarily, that doesn't mean you fully feel comfortable that you understand it. I will re-explain why that is at a certain point. But kinetic energy is always 1F mv squared. Now, potential energy is different for different forces and different contexts. That I definitely have to explain. Potential energy is something that's associated only with certain forces that we regard as conservative. So the spring force is a conservative force. The gravitational force is a conservative force. These are forces that are associated with some kind of equilibrium position, like the spring always wants you to be in the middle. Gravity always wants you to be on the ground. Those forces store energy. Unlike forces like friction and tension and normal, which don't. So they don't have potential energies. But so the spring, so in this case here, so see now I'm in step 4, particularly here, by potential energy, we mean spring potential energy. And spring potential energy is 1F kx squared. Again, that is something I have to explain at some point. But for the moment, I'm saying it. That's true. So I'm still in step 4 here. So step 4 continued. And sure, and this is the part that Remy wants to see, because for sure, once we get into things, it's always usually step 4, that's the longest. Okay, so I'm saying now, so 1F mv squared So all the kinetic plus all the potential over here at x equals 0.15, well, at x equals x naught has to equal all the kinetic plus all the potential over here at x equals 0. Okay, this is what I'm solving now. Now, and I'm looking at the time, like we can go to 7, 10. Yeah, I'm looking at the time. I will tell you right now, because I'm not going to keep you late. I promise you that. I know you have a lab next Tuesday. So this is one of those times apparently I don't have time to actually get you set for that. But Professor Tally will. Like, it'll be understood that you're going in, that she's going to explain to you right away I think you're used to the lab procedure now. So she'll tell you what the lab motions are that day, and you'll do them. And I think you know how to do that. So, and I think you'll be fine. But it will be understood that we didn't get a chance to talk about that first. She'll know that. So we'll all understand that. And I think you'll be fine. But okay, so here we are. We're going to now solve this equation for this problem. Now, here's an example. When we do step 4, one thing I should have emphasized before when I was reviewing, step 4 is about doing the physics and doing the algebra. Like I said, making something that the reader could follow, whether or not they have the actual question right in front of them. This means, like I was yelling about a lot before, we're going to postpone numerical values as long as we can. The last thing we're going to do is actually plug in the numerical details. We're going to try to do as much physics as we can before we actually plug in the numbers. Partly that's so that even if we make a calculation error, like maybe Remy did, I don't know, we'll find out. But if we accidentally did a calculation thing wrong on our calculator, or we got a number wrong, it won't matter as much. We won't lose as many points because we're first going to just focus on the physics. So what am I saying? I'm saying this first. So I look at x equals x naught. I look over here and I notice over here at x equals x naught, the v is nothing. It was given as 0. There's no kinetic energy over here at x equals x naught, which is so there's no kinetic energy. I'm comparing that over here to x equals 0, the equilibrium. Well, when x equals 0, for sure, x equals 0. So first, before I plug in any numbers, I can cross out 2 terms. And I'm going to say, okay, so I have, so far I have 1/2 kx naught squared equals 1/2 mv squared. Now notice again, I should have also made clear, v is the thing that I'm solving for. V is what I'm solving for. I'm solving for the v at x equals x naught, right? That's what I'm solving. Sorry, I'm solving for v at x equals 0. But what this statement right here says is all the potential that was at x naught, all the potential at the beginning, all gets converted to kinetic at the end, right? So before I plug in numbers, I also now, I see that I've got a 1/2 on each side. So I can divide both sides by 1/2, or I can multiply both sides by 2, however you want to look at it. And it can go like that. Right now, I'm almost ready to plug in numbers. But again, remember, I'm solving for v. I'm solving for v. So I'll isolate, I'll do the algebra. I'll just write this again. This is all part of step 4. Like I have kx naught squared equals mv squared, right? That's what I have so far. But I'm looking for v. So let me rearrange. I'm looking for v. That's what I'm solving for. So I rearrange it, right? I'm looking for v. So I'll divide both sides by m. Again, I'm postponing the numbers as long as possible. And I'm looking for v. So I'll square both sides. Now I've got an expression. Now notice this is all correct physics. Even if I don't know the numbers, I could publish this article right now. If you want to calculate the speed at the equilibrium point of a mass that started over here at x naught, this is how you do it. Like, I'm not saying you should memorize this formula. Don't. But I'm saying this is now an equation that's always true. but we just derived it. So now I plug in the numbers. Sorry, and it's going to be a square root of like funny numbers. So I'm going to have to I'm going to have to chop off digits somewhere. It's not going to be a it's not going to be an exact whole number, but I get 200 times 0.15 squared all over 0.3. So I'll go to the next page. And I'll go back a page if you want in a second. I'm just going to write this before I forget. So I'm just recopying this. We have 200 oh yeah. Right, that's what we have. So all right. Well, I guess, okay, so these were all right. I guess this is true. And this, the reason I'm saying approximate, so I get the square root of 15, but that's not the square root of 16. Like 15 is not a, it's not a perfect square. So I get, I'm just doing this to 3 significant digits. So this is what I get for question 4. And I'm going to pause as long as we're cool that you'll be fine on the lab. I think, so let me pause for a second. I think actually we're doing well. I feel like we're doing a lot this class. I mean, I hope you feel that way. And you've been very, very attentive and you didn't even get a break. I'm aware of that. But let me ask honestly, and let me change the view. Let me ask honestly, since Remy is the one that asked for that, and I appreciate it. It could be anyone, right? Like it's not, and again, I appreciate that. I feel like you guys are distributing your participation in a nice way. Like sometimes it's about one person, sometimes it's about another. Hopefully everybody's getting something out of everybody, but I'm just going to ask, since Remy did ask for this, Remy, does that address, I don't know, does that help you find what you were looking for?
Yeah, I usually like put the numbers in first, but I'll try it this time next time.
Oh, okay. No, I appreciate your honesty. And yeah, to everybody, it was a good example for him to ask about 4. And again, I can go back to 1. You can also privately admit to me or whatever, any of you, if it was a mistake to skip 1 through 3, let me know. But 4 is a good example because look, 4, almost everybody would plug in the numbers first for 4. 4 is just long enough or hard enough that almost everybody would want to plug in the numbers first. But 4 is just manageable enough that if you guys try and force yourself to go against your instinct and not plug in the number first, you can do it with 4. Like this is a good example of where to practice doing a new technique, and it will serve you well on even harder problems, I feel. I mean, anyway, I don't want to oversell it, but yes, I do. But okay, I do think that's the answer for 4.
I am like, can you go back 1 slide, please?
Oh yeah, absolutely, of course, yeah. Okay.
So where did the 1/2 go?
Oh yeah. Oh, good question. I'll go back 2 slides. It was there, but if you look at the bottom of this page now, so we had the 1/2, but we had 1/2 kx squared equals 1/2 mv squared. So there was a 1/2 on both sides. Therefore, I could multiply both sides by 2, or I could divide both sides by 1/2, and therefore they both go away. Like they cancel out.
All right, got it.
Cool. Okay, and I think this is, as long as we're doing this, I think for real closure and concreteness and you know, because we've all worked so hard at this. I know what you think I'm going to say. I'm not. I'm going to. I think in 4 minutes I can do the next one, and we could still go 5 minutes early. I think it'd be really worth it for me to just tie this together and just do the next one. In other words, question 5. I'm going to show you all, now that we've done all this hard work on question 4, question 5 goes much faster. Question 5, like, here we go. I think I could do this fast. Like, question 5 for diagram, see above. Okay, so that's step 1, right? It's the same diagram, in other words. That's step 1. Okay, then so what is the question for question 5? The question is, when V equals 3, X equals, right? That's the question. What is, so all that English reduces to, when we actually achieve a velocity of an instantaneous speed of 3 meters per second, what is the position where that happens? And notice it's actually now might seem like a slightly more reasonable question, because what we have so far is a mass that started at a speed of 0. It started over here, 15 centimeters with a speed of 0. It started moving in, getting faster and faster and faster, gaining kinetic energy until it got to the equilibrium position, at which point it had a speed of 3.87 meters per second. So it passed all the values in between along the way. It went from 0 to 3.87. So somewhere in the middle there, it achieved a speed of 3. The question is where? So it's exactly the same type of question as the last one, only the last one we said, what is the speed at this particular spot? And this one we're saying, what is the spot for this particular speed? It's literally the same thing. We're just asking for a different variable. So I set it up the exact same way. I'm going to say again, the GDP is total energy over here equals total energy over there, right? That's my step 3. I don't know why I didn't mean to write that in red, but whatever. Step 3. So in other words, just like before, I'm going to say 1/2 mv squared plus 1/2 kx squared at the beginning when x equals x naught must equal 1/2 mv squared plus 1/2 kx squared at the x that I'm looking for, that I don't know, right? So before I compared 2 spots, the known spot of x naught to the spot that I was solving for, x equals 0. Now I'm doing the same thing again, only I'm literally solving for x this time, right? I'm going to do the same. So that's my step 3. I'm now going to, I know I'm going a little fast. I'm now going to start step 4. I'm just writing out what I had already. 1/2 mv squared plus 1/2 kx squared over here equals 1/2 mv squared plus 1/2 kx squared over there. Now I'm going to go through and try to simplify like I did before. Okay, at x equals x naught, v equals 0. We said that before. Same thing as before. This equals 0. So that term is going to can't die out. But then if I look, sorry. I'm solving for the x that I don't know. So at the x that I don't know, x is not 0 anymore. Like in the other problem, I was comparing to x equals 0. Here, I'm comparing to the x that I don't know. So x doesn't equal 0. So I can't cross out that term anymore. So I'm starting with the same GDP, you see, but when I'm applying it to the particularities of this example, it's not as simple. I can't cross out as many terms. I could still solve it though. What I have is, I have 1/2 k x naught squared equals 1/2 mv squared plus 1/2 kx squared. Looks like I have a 1/2 kx squared on both sides, right? And I'm watching the clock, I promise. So we're not going to go early, but we're not going to go late. Next time we'll go early or something. it looks like I have the same thing on both sides, 1/2 kx squared, but no, on the left, it's x naught, the known position of 0.15. On the right, it's the x that I'm looking for. Okay, so they're not the same thing, but I can factor out a 1/2 from both sides, just like I did before. I can factor it out, right? And then divide both sides by that 1/2. So it does die out just like before. Okay. Now I'm solving for x. I'm not solving for x naught. I know what that is. I'm solving for x. So I'll get it by itself. X squared, kx squared equals kx naught squared minus mv squared, right? I'm solving for x. So I'll divide both sides by k. Now you might think the k's cancel out, but they don't, because I couldn't factor, because there's no k in that second term. Like they could only cancel out if I could factor them out from every term. So I have this, right? I'm just about done, and we're just about done. It looks all complicated, I know, and I'm encouraging you to develop this new habit of keeping it complicated until you plug in the numbers. Because again, all this physics is correct, even if we mess up the numbers. So I'm just going to, but we have one more step and then we're done for today. And you've all been very patient, and hopefully we've all learned something, whatever. So we have x squared equals k. I'm just rewriting it so we have it. We have all this over, okay, right? So therefore x equals the square root of all that. So x equals the square root of all that. So now I'm plugging in 200 for k, 0.15 for x naught, 0.3 for m, 3 for v. Where did I get 3 for v? Because that's what the problem said. It said I'm solving for the x where v is 3. So it's this particular question said that v equals 3 and k is 200. It doesn't cross out because it's not in every term, so it doesn't cross out. And because I'm telling you now, because class is just about over and I don't want to keep you late, if you do this out on a calculator, I mean, I could do one more step, but it's going to squeeze the board and we've got 2 minutes. If you do that on a calculator, you will get approximately 0.095 meters. And when I say approximate, it's not because I'm lying or guessing. I'm not guessing. I'm just saying that the square root isn't perfect, so I have to chop off digits after the 5. Oh, sorry, Ashton, yes.
So, what is stopping me from using the same formula we just did for the 1/2 mv squared? Yeah, the 1/2 kx squared equals 1/2 mv. Like, what's stopping me from using that instead of this formula? Because I did that and I got something different, so I was a little confused.
Wait, I think you should. Wait, which?
So, but like, if you use that formula, where'd you get the second k from?
Wait, oh, wait a minute. Okay, this is a great question. If you mean, what's stopping you from just saying 1/2 mv squared equals 1/2 kx squared? Is that what you're saying?
Yes.
Oh, great question. What's stopping you is that that's not the form. See what the formula was, what the GDP is 1/2 kx squared plus 1/2 mv squared over here equals 1/2 kx squared plus 1/2 mv squared over there. Like the formula, if you like, is that the total energy over here equals the total energy over there. That's what's true for both of these questions. In the first question, we crossed out 2 terms because we said, oh, well, over here at the beginning, there's no kinetic. And then over here at the end, there's no potential because it got all the way to the end to equilibrium. But in this question, we're not getting all the way to equilibrium. We're solving for a spot x that is not 0, that we're solving for a spot. In other words, the spot that we're solving for here, there's some kinetic and there's some potential. This is a very good example of like starting with a truth and then making it relevant. The truth was that kinetic plus potential at any one spot. must equal kinetic plus potential at any other spot. But it happened in question 4, in the particulars of question 4, one of our spots, there just happened to be no kinetic at all. And at the other spot, there happened to be no potential at all. So we ended up saying all the kinetic over here equals all the potential over there. But that wasn't the formula. Like, that wasn't the GDP. That was a particular thing that happened in question 4, that we picked 2 special spots that each had a 0 associated with, like one spot had no potential and the other spot had no kinetic. Here in question 5, one spot, yes, had no kinetic, but the other spot, there was both types of energy, kinetic and potential. Am I making any sense? Or do you, like, what oh, sorry.
A little bit. I'm a little confused.
Well, I'm saying honestly, if you ever wrote down 1F mv squared equals 1F kx squared, what I'm honestly saying is that is not actually a formula. That's not actually an equation that we should have started either question with. That's a result that you got to by the middle of question 4. But saying 1F mv squared equals 1F kx squared is literally not actually a formula. Like, that's not actually true. It's
Oh, got it. I was just thinking like it was a formula. Got it.
okay. All right, cool. All right.
I don't know why my brain went to that, but
No. It's because it ended up being true in question 4. You're not crazy. And it's a very common, okay, wait, sorry. I don't want to keep you because I know it's, but that was a great question. Hold on. Going back, wait, you asked, there's things happening in the chat. This is awesome. Hold on, someone's asking in the chat. Can I go back to step, wait. Can you go back to step 3 when you get a chance? Step 3, yeah. And by the way, I owe you, these questions are so great, guys. And I know it's super late. I'm totally noting that you guys are here overtime asking really good questions. I'm promising you right now, just like last week, I promised we would get to this homework today, and we did, right? I don't break my, next week, we will go early. We will go, like, I owe you a little time now. I appreciate so much that you're making sure you get this before we go. You can remind me next time that I'm promising we will go a little early, like earlier than early, because I owe you the time. But I just think this is too good that you're doing this. So just hang with me for a second. Can I go back to step 3 when I get a chance? Is this what I mean by step 3? Is that what you mean by? Okay, and Eugene's wait. Okay, so super quick. Kayla, is this the page you want me to do, or the net, or do you mean, is that the page you want? Wait. And then I do want to answer Eugene's question really. Again, I will, yeah, okay. So, because honestly, everybody, just so you know, I will answer Eugene's question and then we'll like end on that. And I do owe you some time and praise and A+ and Hello Kitty puffy stickers for everybody. Like, really, did I just say that? Yes. But on the thing that I just want you to know that what Ashton just asked, like, she's being apologetic and saying like her brain is fried because it's the end of the day, which it is. But honestly, she honestly just asked the question that is the whole purpose of question 4, and actually the whole purpose of this whole GDP thing. Like, most people throughout the last 30 years that I've been assigning this problem, honestly, most people get question 4 or 5 wrong. A lot of people get question 4 right because they write down 1F mv squared equals 1F kx squared, which is what Ashton's thinking. Like, she's being polite about it. But the honest thing is, most people think that 1F mv squared equals 1F kx squared is a formula. And I'm here to tell you, she's not crazy. I mean, Ashton is not crazy, but it's not true. Like, the principle is that total amount of energy over here must equal total amount of energy over there, which means all your kinetic. Anyway, I'll repeat this again next time, but I'm just saying the Ashton thing is not a sidebar. It's like really the purpose. It's a perfect example of this whole thing where we really want to know that what's true is the conservation of total energy. And what turns out to look true in certain particular examples is it looks in certain examples that kinetic equals potential. So we get fooled into thinking that that is a general truth, but it isn't. It just happens to be true when you look at 2 points that are special, where one of them has no potential and one has no kinetic. So question 5 is designed to force us to see that if you start looking at arbitrary points, you have to be more careful about what your GDP is. But the true GDP really does apply to both questions 4 and 5. Okay, I'm yammering too much now on you. So, but that's why it's good that Kayla asked me to go back and show that page. That's the page that applies to question 4 and question 5. On Eugene's thing, okay, very fair question on significant figures. It's true. We're much more intense about them in the lab than on homeworks or exams. My general rule of thumb about sig figs on exams and homework is it's like the opposite of what you do in the lab. What I'm saying is use the greatest number of sig figs that was provided in the question is what I tend to keep my answers to. So like the question provided 200 newtons per meter as a K, right? So that's the most number of sig figs that I saw anywhere in the question was 3 of them, 200. So I'm putting all my answers to 3. If we were in the lab, you'd do the opposite. You would only go the significant figures. You'd only go the least number of significant figures that was ever provided in the question. That would be correct in the lab. I honestly, on homework or tests, I think we should go to the greatest number that was ever provided. So I'm going to 3. But if you did something else that's a little bit different, I would not be. I just want you to be consistent and care. I want you to just basically be consistent about significant figures the way you do them in labs, in exams and homeworks. You don't have to be super crazy about them. That's right. Okay. That's a great question. Okay. Okay. Wait. Sorry. Okay. So I owe you time. You can remind me next time. I will talk to Professor Talley about your lab before you do it. I think you guys are doing great. Seriously, just keep up the good work, and I will keep up giving you points and have dinner. And if you have questions, I'm here. I'm not leaving. I mean, I'm here, but you go. But if anybody needs anything, I'll stay until the last person goes for a few minutes. But it's been a very long day for everybody, so please go, and I'll post the video and the PDF and all that. Yes, have a good night. Have a good night. Okay, have a good night.
Thank you so much, Professor.
Thank
Good
you.
night.
Thank you.
Are you available tomorrow, Professor?
Sorry, am I what?
Available tomorrow? I'd like to text you about 7 and 9.
You could definitely, thank you guys. Have a great, let me just turn off the recording. So sorry.